Hi, welcome to Lecture 8 of EEE 107. This lecture will have two parts and we'll talk about the effect of noise in our analog modulation techniques. Okay. So recall your band-limited additive white Gaussian noise channel. Basically, we model the noise as additive, so the noise will add to the transmitted signal. It's white, therefore its autocorrelation is a delta function that's dependent only on the time delay. And it's Gaussian because the noise is normally distributed. Okay? The consequence of it being white is that the frequency spectrum is constant over all frequencies. So at all frequencies, you have the same power spectral density. Now, if we pass it through a filter with a bandwidth that is equal to 2W, you get a band-limited additive white Gaussian noise. And that is now your signal. Right? So your signal, your transmitted signal has a bandwidth 2W, right? And the noise will be added, but after filtering, then you have this amount of noise that is impeding your transmission. Okay? So now let's look at the behavior of noise in bandpass systems. Can we represent the noise in terms of its complex baseband equivalent also? Let's look. So we have a white noise fed to an ideal narrow BPF centered at FC. So that is already a bandpass noise. So the power is equal to N naught times the transmission bandwidth of your system. We can decompose it to its in-phase and its quadrature components. In a similar way, we decompose any type of signal into its in-phase and quadrature component. Okay? So your noise signal, your bandpass noise signal, has a cosine component and a sine component, right? The in-phase and quadrature component. And we can represent this noise here to a complex baseband noise. Okay. So now, if we compare the performance of the different analog modulation schemes, how do we do that? Maybe the same level of noise? Is it that, or is it a fair comparison? So let's see. This is the block diagram of a generic communication receiver. You have a modulated signal, transmitted signal, you add noise, then you do some processing, and then your bandpass filter, because you want to filter out the noise, if you want to reduce the power of the noise that is impeding your transmission, then you pass it through the modulator. The modulator is dependent on how you implement your system. Okay. Before the modulator, you have a signal-to-noise ratio. We call it the pre-detection SNR. And after demodulating, after processing everything, after doing some signal processing, you have an SNR at the output. We call it the post-detection SNR. Okay, so where do we measure the SNR for a fair comparison? Well, we don't measure SNR to compare them. We measure what we call the figure of merit. Okay? So we use a reference SNR for that. To fairly compare your different modulation schemes, we need a reference baseband transmission model, which transmits the message directly. So this is the model. Your message is transmitted with the same power as x of t, and then you add noise to that, and you have a low-pass filter with bandwidth equal to the bandwidth of the message. And you have a recovered message right here. This will be your reference SNR. Okay? It will be equal to the average power of the message signal, this one, divided by the average noise power after filtering. So it's the filtered N of t. So we can use that reference SNR, and we can define what we call a figure of merit, where we use the reference SNR to normalize the post-detection SNR that we will get. Okay? For example, let's look at the noise in a coherent detection scheme. The coherent detection block diagram looks like this. So first, we have a band-limited AWGN. Okay, the bandpass filter is there to limit the noise, but it does not distort the signal in any way. So you have y of t. That's y of t has your transmitted modulated signal and the filter noise. You put that in a detector, which is defined by this block diagram. This is your coherent detector. Okay. So the pre-detection SNR for DSBSC is equal to this. So it's equal to the power of your transmitted signal divided by the power of the bandpass noise, which is equal to this expression right here. So your DSBSC signal has this power, AC squared PM over 2, and the noise power is equal to N naught times the transmission bandwidth BT. Okay, so this is the pre-detection SNR for DSBSC. For SSB, if you have SSB, because we know that the power of SSB is half the power of DSBSC. If we use the same coherent detector, then the pre-detection SNR for SSB is equal to this. Okay? Just a note, however, that the transmission bandwidth for SSB is half the transmission bandwidth of DSBSC. So the BT here are not the same. Okay? So post-detection SNR for X of t, let's say for a DSBSC signal, the signal output at the bandpass filter is equal to this equation. So this is the signal that will be fed to a demodulator. So if we multiply this with a cosine carrier and we put it in a low-pass filter, so it's this operation, okay? Just a note that if we multiply cosine to both a cosine and a sine, this cosine times cosine will have this form. This cosine times sine will have this form. And you'll end up with this equation right here. And since we're using a low-pass filter, all the high-frequency components will disappear. Okay? And you'll be left with this expression. Okay? And this is the demodulated signal. It has the message, and then there's also some noise that's left. Okay? So the demodulated signal can now be expressed as this, and only the in-phase noise is present. So the post-detection SNR is now, for your DSBSC, you have 1/4 AC squared P sub M. That is the power of this signal right here. And your noise power is now equal to 1/4 2N naught W. Okay? Where W is the transmission bandwidth of the signal. So it's equal to this. And now we can get the figure of merit. If we have a reference of the reference of a DSBSC, to get that, you it's not shown here, but let's walk through it. Okay. So a reference transmission for DSBSC, you have a message here with the same power as X of t, and you add noise to that. Okay, and then you pass it through a bandpass filter, low-pass filter with the same transmission bandwidth as, with half the bandwidth actually of your, with some bandwidth W, depending on your message signal. Okay. So it's the same bandwidth as your message signal. It's baseband equivalent, rather. So just recall first that for a bandpass signal, right here, oops. So the bandpass signal has this transmission bandwidth, okay? But if we convert it to a baseband signal, the bandwidth of your signal will now be W. Okay? So we pass it through an LPF. We have an output signal here. The message would still be the same, but your noise will now be filtered out by the LPF. So the reference SNR is equal to the power of the message that is the same as x of t. So that is AC squared over 2 p sub m. Okay. And the power of the noise, the filtered noise, is dependent on this. This is 2W times n naught over 2. We have n naught W. Therefore, the reference SNR is equal to AC squared p sub m over 2 n naught W. Okay? And that's what happened here. And you get a figure of merit equal to 1. Okay? Now, for an SSB signal, the SSB signal can be expressed as this. With a narrow band noise, the signal can now be represented in this way. You have an in-phase and a quadrature component that is impeding both the in-phase and quadrature component of an SSB signal. However, after LO multiplication plus low-pass filtering, the quadrature component actually is removed, and you'll only get this part of your this part of the spectrum, or sorry, this part of your SSB signal. Okay? So post-detection SNR can now be calculated. Note that only one sideband is used in the transmission. Therefore, the transmission bandwidth is equal to the message bandwidth. Okay? So after coherent detection, this is the effective spectrum for the message signal and the noise signal. So the figure of merit here, the post-detection SNR is equal to this. The reference SNR, to compute that, let's use the same process as computing the post-detection SNR of the DSBSC signal. So again, we draw the block diagram. This is m of t, but it has the same power as x of t. And this is your noise signal. And then you pass it through a low-pass filter that has a bandwidth W. And then you have m of t plus the filtered n of t. So m of t has a power the same as your transmitted signal. So that's 1/4 AC squared p sub m. The power of noise here, in this case, is equal to n naught times W also, since you have an LPF with a bandwidth W. Okay? And you get the same reference SNR as the post-detection SNR. You have a figure of merit equal to 1. So what that tells us is that the performance of an SSB signal is the same as that of a DSBSC signal. Okay? So that is in terms of noise, resistance to noise. So the performance of SSB is the same as DSBSC. Okay? And that is the end of the first part of the lecture. In the next part, we'll look at a full AM wave, an FM wave, and a PM wave. Right? So if you have any questions or if you need clarifications, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.